Yes, sir.
Yes, sir.
Okay, so let's begin the lecture. And today's lecture, the agenda is media access in wireless network, mobile network, and then we'll start the wireless LAN 802.11 protocol, which is very commonly used everywhere. So it is- now we have already seen CSMA-CD. If you remember what was CSMA-CD, there used to be a channel like this, and nodes used to be connected. So what was the protocol in the wired network? That was carrier sense multiple access with collision detect. Any node which wants to transfer will first of all listen to the channel, and if nothing is available, will transfer the data. And then the sender keeps on listening to the channel. If in the meanwhile any other fellow transfers, so there would be collision, and sender comes to know that there is a problem of collision. And in that case, what sender used to do? Sender used to send a jamming signal so that everybody can know about that uh, there was a disturbance in the channel. And this keeps on happening. Everybody used to do this before transferring, will sense the channel and keep on sensing the channel for the collision. And then we have seen there was rule that how anybody can be very sure that it has acquired the channel or something like that. Now, what if we try to do the same thing in wireless network? Suppose there is a node A, and obviously if it's a wireless node, the node is going to have a range. Normally in wireless, any node is going to use an omnidirectional antenna. Omnidirectional antenna means that the power of the transmitter would be equal in all 360-degree direction. So if you have any antenna, suppose this is an antenna, so what would be there? There would be a spherical range around that antenna. And if you take the crosscut on the ground of that sphere, so that's why we say that every wireless node is going to have a roughly circular range of the transmitter. So this is what, first of all, we need to understand, that once we are trying to do a wireless communication, every transmitter is going to have some certain range. And that depends upon the power of the signal, power of the transmitter. If the power is more, the range would be more. If power is less, range would be less. So let's try to do the same thing in our wireless node. Suppose there is a node A who is having range like this. Suppose there is a node B who is also having range like this. Suppose there is a node C who is having range like this. Now, let's take one example that B is transferring to A is transferring to B. This particular communication is going on. A is currently transferring to B. A cannot transfer to B right now because range of A is finishing here. So for doing this, you need to have A be in the range of A. So these are the smaller point you need to be very careful about. There is always going to be range of transmitter. Receiver does not have any range. So if A wants to transfer to B, B should be inside the range of A. So let's draw this figure once more in a proper manner. So let's draw A, and range of A would be like this. Suppose there is a node B, range of B would be like this, which is covering A also. And suppose there is a node C, so range of C would be like this. Suppose this is the situation. So A's range cover B, B's range cover both A and C's range cover B. Now let's take our scenario. Currently A is transferring to B. So there are channels, wireless channels. All A, B, and C are transferring on same frequency, same encoding. Everything is same. Similar to the wired example where everybody is transferring using the same frequency and same carrier and same encoding. Now A to B transfer is going on. And at this particular moment, suppose C wants to transfer to B. Now C will do what? If we try to follow CSMA CD here also, what C will do? C will sense the channel. Now, if C will sense the channel at this particular moment, what will happen, Priyav?
Sir, the data will frequency will change.
Think over it. A is transferring to B and C wants to transfer to B. So before transferring, C will sense the channel. What C can sense? That's the question. What C will find? Now let's take the same example on a wired network. Suppose there is A, there is B, and there is C. A is transferring to B. And if C senses the channel, what will happen? Priyav.
It is not the correct destination, so it will also it needs to reject the signal.
But will C be able to sense that something is available or channel is busy?
Yes, sir.
In wired network, if C senses the channel while A and B conversation is going on, C will figure it out that channel is busy. So C will not transfer. That's the CSMA-CD protocol. Remember?
Yes.
Now here the same thing we want to deploy. A to B transfer is going on. A is transferring a file to B wirelessly, and C is now trying to sense the channel. What will happen here? C will find medium to be busy or free. That's the question. Hmm? Anybody?
free,
Why free?
because the receiver does not have a range, so it cannot sense data from A to B.
That is correct because the range of A is up to this point only. You can see this is the black circle. Range of A is here only up till this point. Okay, this is the range of A. Got it? And C is out of the range of A. So when C will sense the channel, C will find that channel is free or medium is free. And according to CSMS-CD, if the channel is free and any node wants to transfer data, now C start transferring to B because C has found out that channel is free. C will start transferring data to B and now there is a collision at B. B's receiver will receive two transfers, two signals of same frequency at the same time and there would be a collision. Any confusions here? Yeah, Priya,
No, sir, no confusion.
got the point?
Yes.
Now the another problem is if there is a collision, the collision is a very transient thing, as we have already discussed last year. Transient. Collision will not be able to reach this collision happening will not be able to reach both to A and C. So actually, carrier sense is failing here, and there is no question of collision detect. And that is the difference in wireless media and wired media. In wired media, CSMS-CD is easily deployable. But in wireless media, due to the ranges of transmitter, it is not possible. Now, this particular problem is commonly known as hidden terminal problem. Very common problem in wireless uh, methodology that is known as hidden terminal problem. C is hidden from A and B. So let's see these things in slide also. If we use CSMS-CD, carrier sense multiple access with collision detection, which we have already seen, that send when medium is free, listen to medium if collision occurs. This is how IEEE 802.3 works. But in wireless network, signal strength decreases with distance. If sender applies carrier sense and collision detect, collisions are going to happen at receiver. Sender will not be able to hear the collision. CD does not work. And due to hidden terminal, carrier sense might not work. So this is the hidden terminal problem. A is sending to B. See the figure. A's range is this violet range. A is sending to B. C is out of the range of A. C cannot hear A. If C wants to send to B, C senses a free medium, which is not the case. Medium is not free. Hence, CS fails. Now, if C starts sending, there would be collision at B, and A cannot receive the collision happening. So collision detect also fails. And in this way, we can deduce that C is hidden from here. This is the problem of hidden terminal. Any questions here? Any doubts? Now let's see the another case. Let's see one more case. So I'm again drawing some nodes, say A, the range of A is like this. Then node B, sorry, this is node B. B's range is like this, red one. Then node C, C range is like this. And then there is another node. Let's see, there's a node D, and D's range is like this. Now let's see the situation. Suppose B is currently, node B is transferring to A. See it carefully. Node B is currently transferring to A. This is going on. And C wants to transfer to D. What will happen? Anybody?
Sir, the medium is free, so it can just transfer.
I'm trying to say that C, if we are deploying CSMA CD,
Sir, C will try to sense the channel, and since it is lying in the range of B, so it will see that the medium is not free and it will not send anything.
it will not. But it can perfectly send. C will find that medium is busy, but actually C can perfectly send to D because D is not currently in transfer, is not receiver for anybody. Yes or no?
Yes.
But C will not transfer if the CSMA CD is getting deployed. C will not transfer because as and when C senses the channel, C will find the signal available because C is in the range of B. So C will stop. C will not start transfer to D, which can be perfectly done. So in this case, another problem comes, that is the problem of exposed terminal. And what is that problem? Just see here. B is sending to A. C wants to send to another terminal, not A or B. When C will sense the channel, C finds that there is something available. Something available because C is in range of B. C will find that medium is busy. But A is outside radio range of C. Fine. Because you are not transferring to A, you are not transferring to A, which is receiver right now for the conversation between B and A. A is out of the radio range of C. C can perfectly transfer to anybody else apart from A and B. But C will not transfer because C will find that there is a signal available because C lies in the range of B. That's why C is exposed to B. So there are two problems in wireless. One is hidden terminal and other is exposed terminal. Any questions here?
Yes.
In one case, carrier sense fails and it resulted in collision. In another case, carrier sense fails because it is not allowing to transfer to a perfectly fine system. Now, due to this problem, a protocol came that is known as MACA, that is multiple access with collision avoidance. So what is that protocol? CSMA CD. So we have just removed CD. CD is of no use. Carrier sense is of no use. So what remains? MA, medium access with collision avoidance. MACA protocol. Multiple access of medium with collision avoidance. Now what it has proposed that before transferring any real data, you use some control packets. Two control packets. One is request to send RTS. Before transferring any real data, sender will use RTS to request write to send before it sends any data packet. When a receiver receives an RTS, receiver will grant the right to send as soon as it is ready to receive. And that particular control message is known as CTS, clear to send. And these control signaling packets contain sender address, receiver address, and the packet size. How long the medium is going to be busy is going to be known by packet size. Request to send before transferring any real data packet, and receiver will send a clear to send, and by this receiver will grant the right to send as soon as it is ready to receive. And then variants of this method we'll see later on that can be found in 802.11 as distributed foundation for wireless medium access control. We'll be seeing in detail DFW MAC. So let's see, using RTS and CTS, can we solve the hidden terminal or exposed terminal problem? Let's see that example. Let me draw that again. A, then B, range of B, then range of C, now what is happening? We are trying to solve hidden terminal problem. So A wants to send to B. A wants to send to B. Before A can send anything, A will send a RTS packet. A will send RTS. Now this RTS contains sender address, receiver address, and packet size, which actually tells about NAV, network allocation vector, how long the channel is going to be occupied. Now, once A send RTS, this RTS will be available in whole range of A. But because RTS is having receiver address as R, so B will receive this RTS packet and accept that RTS packet. After getting the RTS, B will do what? B will send a CTS packet, CTS signal. Now CTS is also going to have sender address, receiver address, and this NAV of RTS will be copied here. Now, when B sends CTS, the CTS will be available in whole range of B. What will happen? C will be able to overhear this CTS. And C will be able to overhear one more thing, that how long this network is going to be allocated. So here you are not required to sense, C is not required to sense the channel, because after overhearing this CTS detail, C can know that there is a conversation going on between A and B, where B is the receiver, and this conversation will go on for this time. So C will not transfer the packet to C. So this is kind of virtual carrier sensing. It's not a physical carrier sensing, it's a virtual carrier sensing by using CTS. Any questions here?
Yes, sir.
Any question by anybody?
Sir, how initially we can get, how much time it will take to transfer all the packets?
Yeah, that depends. That depends upon what type of wireless channel you are using. Every wireless channel is having its own bandwidth. Fine. And as a sender, you know that how much data you are going to send in this frame. Fine. So that's how you can actually kind of uh, estimate the network allocation vector. Any other question? So let's see in slide. MSCA avoids the problem of hidden terminal. A and C both wants to send to B. Suppose A sends RTS first. Fine. B replies with a CTS. The CTS will be overheard by C also. C comes to know that there is a transfer going on between A and B, where B is a receiver. C waits after receiving CTS after overhearing CTS from B. Now my question is, can we solve exposed terminal problem? Can we solve exposed terminal problem using RTS and CTS?
Yes, sir.
How?
The same way we already know that it is busy for this receiver, so I can send to any other receiver or sender. Like I just need to check whether the sender or receiver is not my receiver.
So let me draw it and you tell. Okay, let me draw it and you tell from the Priya. Okay, so let me draw the nodes. A node range is this. Then B's range is this. Sorry, B is here. B range is this. Then say C is here. C range is this. Now here what will happen? B is transferring to A. So what B will do? B will send
Yes, sir. RTS.
B will send RTS. So B will send RTS to A. This will be overheard by
C.
C. So C knows. बस इतने से हो जाएगा.
No, sir. Like C wants to send to D, right? So, C
No,
को
no.
पता है,
C wants to send somebody else, not A and B.
sir. So B is sending to A, so C can
Hmm.
send to anyone other than B and A. So like C has heard the RTS in an RTS, it knows that B is the sender, but A is the receiver.
Mm-hmm.
So C can send to anyone other than A, right?
Only by RTS C can judge this.
So CTS will be also there, like A sending CTS to B, but that can't be heard by C.
Yeah, that's right. Once A sends the CTS, the CTS will not be heard by the corresponding CTS will not be heard by C. And then C can be very sure that whomsoever is the receiver is not in my range. Got the point, Priya?
Yes, sir.
So we require both CTS and RTS. So B sends the RTS, C will overhear the RTS. Okay. But she will not be able to hear the corresponding CTS in this case. And that's how she will deduce that whomsoever is the receiver A is not in my range and I can easily send to any other receiver. Got the point?
Yes, sir.
Okay. So let's move ahead. B wants to send to A. B will send the RTS. Now C does not have to wait because it cannot receive CTS from the A. Now let's start our main agenda for today. I'll just start this particular thing today. Let's see how much we can complete. That is wireless LAN. Lot of work has been done in this area. Wireless LAN, and basically when we are talking about wireless LAN, it is for enterprise networks. Mind you, we are not talking about mobile networking here. This is not mobile networking. This is not your 3G, 4G, or 5G. This is not that. Just a minute. अबे क्लास में है अभी. So this is not mobile networking. Now, when we talk about wireless LAN, just keep one thing in mind. Only the last hop, mostly only the last hop is wireless. If you see in our institute also, so there would be wired network with our layer 2 switches, layer 3 switches, and finally at the last hop there is wireless access point. So when we talk about wireless LAN in any enterprise network or in any organizational network, it is a combination of both wired network and last hop is wireless. Means your laptop or your mobile device is connected to a wireless access point. That is the only wireless part. Rest other thing is wired. So your data is going from your mobile to your wireless access point wirelessly, And then from wireless access point to our core switch to internet, this is all wired. Similarly, in mobile networking also, your last hop means from the mobile tower to your mobile phone, this is wireless. But this mobile tower to another mobile tower to the gateway, internet gateway, this all is wired. So whenever we talk about wireless network, mostly it is a mixture of combination of both wired and wireless. Unless and until we are talking about wireless mesh networks where everything is wireless, WMN. So if time permits, we'll be seeing wireless mesh network also. So today's focus and tomorrow's focus is wireless LAN. See here. So if we see the wireless LAN, it would be like this. There would be a infrastructure network, which is shown as a distributed system here. Then there would be a gateway. Using that gateway, you can connect to 802.3 LAN. So you have to do a little bit of bridging here. These access points are connected to the mobile station using 802.11. So in a nutshell, if you see how wireless network look like, so it would be like a L2 switch, which is connected to L3 switch, which is connected to your internet gateway. This L3 switch is again connected to one L2 switch. So this L2 switch will be connected to wireless access point, wireless access point, and these are your nodes. Mobile node 1, mobile node 2, and things like that. Now, if you see carefully, between wireless access point and mobile node, the common protocol which is working is 802.11. And between wireless access point to our infrastructure network, the protocol which is working is 802.3. So whatever 802.11 protocol is working in this area only, from your node, mobile node to the wireless access point. This mobile node can be your laptop, your mobile phone, or something like that. So this wireless access point is actually capable. You might have seen your wireless access point also. Your wireless access point, actually you connect it to a Cat6 cable or Cat5 cable. There is a RJ45 jack here. So your wireless access point in this side is using CSMA CD, which is nothing but our switched Ethernet, which is IEEE 802.3 wired part. And your wireless access point in this side from mobile node to wireless access point, it is using 802.11. And this is known as infrastructure mode. Your wireless LAN card can be in two modes. One is infrastructure mode and other in ad hoc mode. Normally we see our wireless LAN card by default is in infrastructure mode. So what is this ad hoc mode? Ad hoc mode is, suppose there is a node A and there is a node B and there is no wireless access point in between. So what is possible? You can change the wireless LAN card mode from infrastructure to ad hoc, from infra to ad hoc. Here also from infra to ad hoc. And now without access point, this A and B can communicate using 802.11 ad hoc mode. And this is normally known as P2P wireless, peer-to-peer, without the need of any infrastructure wireless access point. So this is also possible. This is also possible. And mind you, this is different from Bluetooth. This is different from Bluetooth. Have you seen any this type of communication, Priya?
In mobile devices?
In mobile devices, you connect to another mobile device directly.
No, sir. Like possibly through hotspot, but only
So
possible.
once you make a hotspot, that hotspot is a wireless access point.
Yes.
Got the point?
Yes.
So this is also possible. You might not have seen. At the most, you might have seen this protocol known as Wi-Fi Direct. Have you heard about this?
It's a direct connection, but it was
So
not.
we'll see it if time permits. First of all, let's see the basics. So basically, there are two modes in which your wireless LAN card can work. One is infrastructure mode, which is most commonly used, and other is your ad hoc mode, where two devices without the need of access point can communicate directly in peer-to-peer manner. That's what you are going to see. Two type of topologies, as I have told you, the ad hoc and infrastructure. The ad hoc topology support P2P connectivity. Mobile nodes communicate directly with each other using wireless adapters only. This is ideal for meetings or setting up temporary work groups. However, it is going to have disadvantage of limited coverage area. So this is how ad hoc wireless LAN is connected. PC client, PC client, PC client. We can connect these three clients in ad hoc manner. Infrastructure wireless LAN, we use an access point that controls transmission and assigns priority levels, monitors network load, allows mobile station to roam from one access point to another access point. It also handles traffic from mobile station to another mobile station. Means if you want to transfer data from A to B in infrastructure mode, A first will transfer to wireless access point, and then wireless access point forwards this to B. So wireless access point works as a wireless L2 switch, kind of. So A and B cannot directly transfer if A and B are in infrastructure mode. So if you want to transfer, even if A and B are sitting very close to each other, the data will go to wireless access point and wireless access point will transfer data to B. This is in infrastructure mode. Now, this is how infrastructure mode looks like. It's a wired network. Access points are connected. Every access point is going to have a range. Fine. And only the last hop is wireless. And cells are normally overlapping. If you change from one access point to another access point, this is generally, if wireless LAN is configured correctly, it is generally seamless. These are the some spectrum which are currently getting utilized for. There are two type of spectrum, 2.4 gigahertz and 5 gigahertz. Both are getting utilized. If you talk about 802.11 standard, it covers both MAC sublayer and physical layer. There are three different physical layers in 2.4 gigahertz band. That is frequency hopping spread spectrum, direct sequence spread spectrum, and infrared. And then there is OFDM based physical layer in 5 gigahertz band. This is all electronics stuff, not particularly needed for ourselves. So if you talk about ad hoc network, the ad hoc network architecture look like this. Nodes which are directly communicating, and then the whole coverage area of this node in which they can communicate is known as basic service set. And that's how you always see a SSID, basic service set ID, when you connect to the any access point. So in ad hoc network, these cells are known as basic service set. This is the basic building block of IEEE 802.11 local area network. The ovals can be thought of as the coverage area within which member station can directly communicate. The independent BSS is the simplest LAN. There's only one basic service set. Fine. And they can communicate using distributed coordination function mode of 802.11. This is the most common mode utilized everywhere. Fine. We'll see distributed coordination function in detail. Ad hoc network, direct communication within a limited range. There is a basic service set. Range is going to be limited. In infrastructure, there would be a wired network and different access points are connected. Every access point is responsible for one basic service set. And the wired part, wireless part, is actually in totality known as extended service set. These are just terminologies. Station is the wireless station, basic service set, access point is the wireless access point, portal, wireless access point itself has a portal to bridge between 802.11 to 802.3. Distribution system is your interconnection network. It can interconnect multiple BSSs, means multiple access point. 802.11 standard logically separates the wireless medium from the wired medium. And it does not actually say anything about that which kind of wired medium or any other medium you require. It just suggests that it is a 802.11 part and it can be connected to any other part depending upon what kind of bridging you have. Now this is where the TCP IP protocol stack is. So this is a mobile terminal. It is having application layer, transport layer, TCP, IP, logical link control. And our focus is this 802.11 media access control. Here it is our focus. If you talk about media access control, we'll be discussing in detail the access mechanism, fragmentation, encryption. We'll be discussing about synchronization, how access point and node can be connected, roaming between different access points, management information based, and power management. As and when we are talking about mobile devices, the power management is going to be a important issue. If we talk about MAC management, physical management, there are two important layers. One is PLCP, physical layer convergence protocol. It is used for carrier sensing. So we have discussed MACA with RTS CTS, but if you talk about 802.11, we are still using carrier sense. So in 802.11, actually it is CS, carrier sense, with multiple access, CSMA. No, there is no MA. It is CS, carrier sense, with collision avoidance, CSCA. So 802.11 works on this concept mostly. There is optional RTS CTS also. We can set up RTS CTS also in our access points and our wireless devices, but mostly 802.11 works on CSCA, carrier sense with collision avoidance. We'll see these things in detail, don't worry. Physical management, channel selection, management information base, PMD, physical medium dependent layer is regarding modulation, encoding, station management, coordination of all management functions. If you talk about MAC layer, there are two types of traffic services. Asynchronous data service, which is mandatory. Every device which is supporting 802.11 has to have this distributed coordination function. There is a time bounded service point coordination function also, which is not mostly used. PCF is not used. Access method, distributed coordination function, CSMACA, carrier sense multiple access with collision avoidance. This is going to be mandatory. Collision avoidance will be done via randomized back-off mechanism. There would be acknowledgement for the unicast packets. So let's see DCF CSMSCA in detail. The three access methods in 802.11, distributed coordination function CSMSCA, which is mandatory, distributed coordination function with RTS CTS, which is optional. Obviously, when you use CSMSCA, there would be hidden terminal and exposed terminal problems. When you use DCF with RTS CTS, which is optional, not every access point and wireless device supports that. It is going to avoid the hidden terminal problem. But normally, mostly, which access method is used? The first one, DCF. PCF is again optional, where access point is a master device and polls the terminals according to the priority or any list. We'll be seeing all these one by one. Carrier sensing. In 802.11, carrier sensing is performed at the air interface, physical carrier sensing, and at the MAC layer, virtual carrier sensing using RTS CTS. So we'll be more focused to the physical carrier sensing because RTS CTS, as we have seen, is a optional method. Physical carrier sensing is was detects presence of other user by analyzing all detected packets, detects activity in the channel via relative signal strength from other sources. Obviously, physical carrier sensing is not going to solve the hidden terminal problem, but 802.11 sort of ignores that. Instead of sending RTS, CTS, and extra packets, it ignores that problem. So it performs physical carrier sensing most of the time. Virtual carrier sensing is done by sending protocol data unit duration information, net allocation vector in the header of RTS, CTS, and data frames. Channel is busy if either mechanism indicate it to be duration field indicates the amount of time in microsecond required to complete the frame transmission. And then station in BSS use this information in duration field to adjust their network allocation vector. So when we are using RTS and CTS and data packet, which are indicating that how much time a particular medium is going to be busy, that is known as virtual carrier sensing. We need to have acknowledgements in 802.11. Fine. I have included RTS and CTS in my slides, but if RTS and CTS is not there, because it is optional, please be very careful about this point. I have included RTS and CTS just to make you understand, but if RTS and CTS is not there, still acknowledgements are going to be there. If A fails to, suppose B receives data from A, B receives any data from A, even if there is no RTS CTS, if B receives any data from A, B will send an acknowledgement. Both C and D will remain quiet until acknowledgement. Otherwise, acknowledgement collision may happen. So if A wants to transfer to B, A will sense the channel, and we'll see how distributed coordination function works. And once A sends the data, B will send the acknowledgement, and then only A can transfer again. When we are using RTS and CTS mechanism, expected duration of transmission plus acknowledgements included in the NAV of RTS and CTS packets. Now just see how it works. Please be with me. It is little bit difficult, and you need to be very careful in understanding this. So let me change the setup for a while. Now, what is going to happen? Any node which wants to transfer suppose this is a node, this is a timeline, this is a timeline. Any node which wants to transfer, which first of all wait for this time unit known as DIFS. Suppose I am a node A, I want to transfer. I'll wait, I'll start my period of DIFS, keep on listing the channel. If I found that medium is free for more than or equal to DIFS, I start accessing the channel. So there are two options. Once node A wants to transfer, node A will wait for DIFS time. What is this DIFS time? I'll tell you. There's a time unit known as DIFS. We'll wait for DIFS. After DIFS, after waiting for DIFS and keep on listening to the channel, if up to DIFS time or more than that, A found that there is no signal available, keep on listening to the channel, then A directly accesses. This is the first case. Now, if during this wait time, during this DIFS time, if A found that medium becomes busy, So A will keep on listening to channel. After medium become free, there is no, if there is a clear channel assessment, it will again wait for DIFS time. But now, because it has already found once a medium busy, and after medium become free, it will wait for DIFS time. Next time, it cannot directly access. It has to choose a random value from this contention window and wait for some more time. Priya, understood?
Yes, sir.
Shall I repeat it? You want me to repeat it? Anybody? Now, means in a nutshell, A wants to transfer, will wait for DIFS. If during DIFS and when it is waiting for DIFS, it is sensing the channel also. If during DIFS, nothing found, access the channel directly. If during DIFS, medium became busy, you again wait for medium to be free, wait for DIFS again. Now enter into a contention window slot. Choose the slot randomly, wait for that much time again, and now transfer. अगर पहली बार में DIFS वेट करने पे कुछ नहीं हुआ तो डायरेक्ट एक्सेस. अगर DIFS वेट करने के दौरान मीडियम बिजी हो गया तो फिर से DIFS जब मीडियम फ्री हो और फिर स्लॉट टाइम से एक टाइम चूज करेंगे, उसके बाद उतना वेट करेंगे एंड देन वील ट्रांसफर. गॉट द पॉइंट?
Yes, sir.
Sir, what is the use of that contention window?
5 लोग हैं सपोज. बच्चा किसने पूछा? नाम बताओ.
Sir, this is Priya Kumari.
Priya, look, suppose 5 nodes are trying to access. They are in range of each other. All the 5 nodes are waiting for DIFS time. If anybody started before anybody else, what will happen? The nodes who are waiting for, suppose, just take one example. Let me draw that example. See here, suppose there are 5 nodes A or 3 nodes or 4 nodes A, B, C and D. All wants to access the channel. A started first. A will wait for DIFS. Nothing will be available on channel. Now A has kept medium busy. B started here. B will wait for DIFS. And during its DIFS wait, B will find that medium is busy. Now B is waiting. Suppose C started here at the same time when B started. B also found, C also will find this thing that medium became busy before DIFS. Now C is also waiting for the channel to become free. Channel is busy. Suppose D also started at the same time. DIFS time, medium became busy before DIFS. Priya, now what will happen? After medium become free here, at this point of time, medium will come free. What B, C and D will do? They will again wait for DIFS. Fine. And as and when they find that DIFS, suppose there is no random contention there, as and when they will find that during DIFS nothing is there, they all start transferring and then there would be a collision. Got the point, Priya?
Yes, sir. Got it.
So to avoid the collision, this particular protocol is carrier sense multiple access with collision avoidance. To avoid the collision, after they have waited for DIFS and then found the medium busy, they'll again wait for DIFS time and then we'll enter into a contention. Randomly we'll pick different waiting time and it will avoid the collision. Fine. Now let's see. Just a minute. Let's see. Station ready to send, start sensing the medium. Carrier sense based on carrier channel assessment. If the medium is free for the duration of interframe space, that is DIFS, interframe space, the station can start sending. IFS depends on the service type. There are different type of IFS, DIFS, PIFS, SIFS. If the medium is busy, the station has to wait for a free IFS. Then the station must additionally wait a random back of time. This is for collision avoidance, as I have discussed. If any other station occupies the medium during the back of time of the station, the back of timer stops. We'll discuss this in detail. Just wait. Now see, this is the situation. Please be with me. There are, sorry, there are 5 stations, 1, 2, 3, 4, and 5. Which station started sensing first? Station 3 started sensing first. This is the timeline. This is the timeline. Station 3 started sensing first. This is the channel. On same channel, all these 5 station wants to transfer. Please be with me. Station 3 started first. Waited for DIFS time. See here, DIFS time. DIFS. And during DIFS, channel was not busy. Station 3 started transferring. Now other station 1 started sensing here. Station 2 started sensing here. Station 5 started sensing here. Station 1 will start sensing for DIFS time, and here it will find, as soon as it reaches here, it will find that medium is busy. Station 2 finds the medium to be busy. Station 5 also find medium to be busy. Now what will happen? All these 3 stations, after station 3 has transferred a frame, all these 3 stations which are keep on sensing the channel 1, station 1, 2, and 5, we keep on sensing the channel. After medium became free here, they all will wait for DIFS. Now station 1 is also waiting for DIFS. Station 2 is also waiting for DIFS. And station 5 is also waiting for DIFS. During the DIFS time, its medium is again free. Now what they will do? They will pick and choose a time, random time. Station 1 got this much time. Station 2 got this random time. And station 5 got this random time. This random time. Obviously, station 2 has got less random time. It will wait for less time. Just a random. Luckily, he got less time to wait. Station 2 will keep the medium busy. Station 1 is waiting for this time. It will find here that medium again became busy. Now, whatever time, waiting time is remaining, that clock is stopped, and this is known as residual time. Means station 1 has to wait for this much more time. Green one. Similar with station 5, residual time. Again, medium will become free after 2 has transferred the frame. Station 1 again wait for DIFS. And now it just wait. It will not choose again the value from the contention window. It will start waiting for BO residual इतने time के लिए जो उसका बचा time था. Station 5 will start waiting for the residual. But in between, station 4 also came, who got this contention period from the contention video. It is a residual time of 5. Unluckily, they both are same and it will result in a collision. So this keeps on happening. This keeps on happening. There would be collision, there would be avoidance of collision, and channel is getting utilized. Any questions here?
And according to the diagram, the DIFs are all in sync for all stations. So is that the case, or it's just shown like
Can you come again?
that? The DIFs times are all in synchronous for all the stations. So is that just showing? It's just shown like that, or is that the case?
Obviously, everybody has to start waiting for DIFS once the medium become free. And they all have to wait for DIFS. That is
Yes, sir.
interframe space.
Is it at the same moment? So like shown in the diagram, or
Obviously,
when
because
okay.
look, station 1 wanted to transfer, no? See
Yes.
here, station 1 wanted to transfer, medium was busy. Station 2 wanted to transfer, medium was busy because station 3 has occupied. So as and when medium became free, they will again start waiting for DIFS at the same moment because they all are sensing the channel also because they want to transfer the data. All these wants to transfer the data. They keep on waiting for DIFS time does not mean that they are waiting idle. They are sensing the channel also at the same time. So as and when the medium will become free, they will start waiting for DIFS. Then we'll enter into the contention window. Take the random time. But there is a small catch here. If you have already waited for some time, whatever random time you have got, next time when you'll get the chance, you'll wait for your residual time instead of again choosing the random value. Got it?
Yes.
Okay. Collision avoidance. Now there are certain points which you need to be very careful about. Collision avoidance. Once channel becomes idle, the node waits for a randomly chosen duration before attempting to transmit. When transmitting a packet, choose a backoff interval in the range of 0 to CW. CW is known as contention window. It is not congestion. Contention window. Now count down the backoff interval when medium is idle. The CW is a nodes variable. It's not a system variable. Every node will be having its own contention window. How it grows, how it goes down, we'll be seeing that. Is if there are 5 nodes, every node will be having its own contention window. When transmitting a packet, choose a backoff interval in the range 0 to CW. CW is a contention window. Randomly pick a value. Count down the back off interval when medium is idle. Count down is suspended if medium again become busy, and that is where you store the remaining time in back of residual. Countdown is suspended if medium again. तुम वेट कर रहे हो back of time, जो भी तुमको मिला हुआ है रैंडम टाइम, उसी बीच में मीडियम बिजी हो गया, तो जहां तुम्हारा टाइम रुका है वहीं पे रोक देंगे. अब तुम अगली बार जो रेजिडुअल टाइम है उतना ही वेट करोगे एवरी स्टेशन. When back off interval reaches zero, either transmit RTS if you are using RTS CTS mechanism, or transmit data directly. That depends upon that which mechanism you are using. DCF you are using or DCF with RTS CTS you are using. See, these are suppose B1 and B2 are back off intervals at node 1 and 2. And currently the CW is 31 in both cases. In both nodes, CW is 31. B1 and B2 are back off intervals. B1 got 25, B2 got 20. Obviously, what will happen? B2 will wait for less time because it has got 20. B2 start transferring data. And at that time, B1 will sense that medium became busy. What is the residual time here, Priyav?
Residual time will be 5.
5. Now, residual time is 5. B1 is waiting because medium is busy. Next time, B2, next time after waiting for DIFS, B2 will again choose from the contention. B2 got 15, but B1 will wait for its residual time. And now B1 start accessing the channel. And after B2 has waited for 5, channel will become busy. Now what is the residual? 10. Next time B2 will wait for 10. Are you getting the point?
Yes, sir.
This is how the distributed coordination function works. I have deliberately written congestion control here. It is not congestion control, it is contention control. One, because it is contention window in distributed coordination function. It is contention control achieved by dynamically choosing the CW. Large CW leads to larger back off intervals. But obviously, if the large CW is there from 0 to 8, means 7 values are there. 0 to 7, 7 values are there. From 0 to 15, 15, 16 values are there. Fine. If seat contention window is big, the chances of collisions are less. If contention window is small, it will lead to large number of collisions. What is binary exponential back off in DCF? When a node fails to receive CTS in response to its RTS or acknowledgement in response to the data. In both cases, the slide is in using the RTS CTS of DCF. But if RTS CTS is not getting utilized, then when a node fails to receive acknowledgement in response to its data, the contention window will be increased. It will be doubled. एक minimum value से शुरू करेंगे, fine, 0, 1. And if there is no response acknowledgement or no response CTS for RTS, the CW will be doubled up for the next round. And the maximum bound is CW max. Now, if suppose you transfer data and you receive the acknowledgement successfully, तुरंत अपनी विंडो को CW minimum कर लेंगे. ये सब कुछ सही चल रहा है. So in this way, every node maintains this variable CW, which the minimum value is CW min and maximum value is some CW max. And if there is no response, means data transfer is unsuccessful, maybe collided, double up the window to avoid the collision further. If there is a successful response, lower down the window, restore the CW to the CW minimum. Fine. Priorities are defined through interframe spaces. This is mandatory idle time intervals between the transmission of frames. ये भाई अपने वार्ड में भी होता है कि तुम लोग ने पढ़ा कभी आईएफएस पढ़ा है इंटरफ्रेम स्पेस जब स्विच डेटा भेजता है L2 स्विच आपको लगातार भेज रहा है when a switch is sending data to you switch is also using some interframe space otherwise your LAN card will not be able to analyze when the frame is stopping and when the next frame is starting. So this interframe space is always going to be there between two frames transfer. In 802.11, there are different interframe spaces depending upon how much priority you want to give, who can access the channel first. It is a mandatory idle time intervals between the transmission of the frames. This is SIFS short interframe spacing, highest priority. तुम नहीं चाहते हो कि acknowledgement and CTS etc. are going to collide. They should not be collided. And that's why if you want to send acknowledgement, you just wait for SIFS time. SIFS time and slot time are fixed per physical layer. Normally for direct sequence spread spectrum, it is 10 microsecond SIFS time and 20 microsecond are the slot time. The slot time of the contention window. Then there is PIFS. When we are using point coordination function, we'll discuss that later. What is point coordination function? PCF, IFS, PIFS, and PIFS time is SIFS time plus the slot time means 10 plus 20 microsecond, it is 30 microseconds. Then there is DIFS, lowest priority. It is DCF IFS, distributed coordination function interframe space. DIFS time is SIFS time plus 2 into slot time means SIFS time 10 microsecond plus 2 into slot time means 2 into 20 in total 50 microseconds. And that's how acknowledgement may win the race, CTS may win the race because they have to wait for less time. SIFS is smaller. So this is how it works. Station has to wait for DIFS before sending data, as we have discussed. So this is a timeline where there is a sender, there is a receiver, and there are other stations. So this is a, let's just a minute. So this is sender, this is receiver, and there are other station contending for the channel. Sender will wait for DIFS. If no data, no medium is not busy, start transferring the data. Now receiver after receiving the data, wait for SIFS. अब इसको प्रायोरिटी मिल गई क्योंकि ये कम टाइम के लिए वेट करेगा and will send the acknowledgement. Other medium, other may lose the race because they have to wait for DIFS, which is way too large than SIFS. Another station, because they have found it to be busy while they were waiting for DIFS here, they will enter into contention window. After DIFS, they will enter into the contention window and then they can transfer the data. If we are using RTS CTS mechanism, sender will wait for DIFS, will send RTS. Receiver will wait for SIFS, smaller time, send CTS. Now sender after receiving the CTS again wait for SIFS जिससे बाकी लोग ना जीत लें and send data. Receiver will again wait for SIFS and send the acknowledgement. Now you can see here after sender has sent RTS, the station who have overheard the RTS will wait for this NAV which is part of RTS header. Sender who have heard the CTS will wait for NAV which is part of the CTS. And these other stations, they will wait for this network allocation, and after that they wait for DIFS and then enter the contention period. So this is 802.11 RTS CTS. There may be a case where your frame is big, then you need to do the fragmentation of the frames also. So what sender will send? DIFS, RTS, receiver will wait for SIFS, send the CTS, receiver will wait for SIFS, sender will wait for SIFS and send the fragment 1, and then there is a option, it will be telling that more fragments are coming. Receiver will wait for SIFS, send the acknowledgement 1, again SIFS, fragment 2, SIFS, acknowledgement 2, and so on and so forth. And other station keep on adjusting the NAV by overhearing the fragment 1, fragment 2, RTS and CTS by overhearing the NAV included in the headers of fragment 1, fragment 2 and RTS, CTS. In this way, they will come to know that they have to wait for some time and then again enter into DIFS and contention period. So we have seen this most important and most commonly used mechanism of 802.11, which is distributed coordination function. In the next turn, we'll see point coordination function and ad hoc mode, that how in 802.11 ad hoc mode works. Any questions anybody wants to ask? Any questions from anybody? Priya?
Sir, so
Yeah.
I have a question. We were talking about the contention window and choosing a randomized value. What if it happens that the randomized value by the two nodes are the same?
That can
What
happen.
happens after?
That
Then
can
what
happen.
happens after? So they have to wait
Collision.
for the same time. So who
Collision.
begins to transmit first?
There would be collision. It is collision
And
avoidance. There would be a collision. It is collision avoidance. You cannot stop. Even in 802.3, there would be collision. Fine. Collisions can only be avoided. They cannot be kind of abolished. If it is a shared media, there would be collision. What we are trying to do, we are trying to avoid as much as possible. We are not saying that they will be completely abolished. Got the point? It may so happen. My contention window, your contention window, me and you may choose the same value. After waiting for the IFS, we'll again enter into collision. As soon as we enter into collision, we'll change our collision window sizes. Both will double their collision window. And now randomly choose from a bigger window. Next time, hoping that we will be getting the different time to wait. Are you getting the point? So if you see the Wireshark, if you see the Wireshark output when you are connected in a wireless mode, you will find that there are lot many packets which are not receiving acknowledgement and you are retransmitting it. You see the number of retransmissions happen in wireless when you see the TCP retransmit in comparison to the number of retransmission happening in wired, you'll see lots of changes. In wireless, there would be more number of retransmission. Got the point? And that's why we have this acknowledgement mechanism that you make just to make sure, because the medium is wireless, whether you are transferring packet, it has been received correctly or not, that depends upon that. Any other question, Amisha?
no, sir, that's it.
So I think we can stop here if there are no more questions. And tomorrow, same time, we'll meet 11 to 1. Thanks a lot. Thank you.
Thank you, sir.